All right, picking up where we left off last class, we were just getting into equilibrium expressions for things that have solids or liquids in them. And you may remember, hopefully you remember, that we exclude those from our equilibrium expression because they are constant, so they just turn into a 1. The concentration doesn't change. So here we have two things that are solids, the calcium carbonate and the calcium oxide. And so we can just ignore those when we're writing our equilibrium constant, our Kc. So our Kc is just the concentration of CO2. Doing another example, write an expression for the equilibrium constant for this equation. Hydrochloric acid reacting with oxygen gas to produce water and chlorine gas. So just like in the previous one, we're ignoring things that are solids or liquids. In this case, we have a liquid, which is water. So we can ignore water for writing our equilibrium expression. We still have to pay attention to it for everything else, but for the equilibrium constant, we get to ignore it. And we do products over reactants. So we've got chlorine gas on the top with a superscript of 2. So concentration of chlorine squared. And then on the bottom, we've got our reactants, hydrochloric acid raised to the 4th power times the concentration of oxygen. Going back to another concept that we talked about, we have two options for equilibrium constants. We've got our equilibrium constant with respect to pressure and our equilibrium constant with respect to concentration. There's a specific set of circumstances in which those are the same. Which of these 3 equations satisfies that condition? Let's take a look. We've got a guess for B. So again, what we're doing here, the time when these are equal is when we have equal moles of gas in reactant and product. So it'll help us here, especially if we got this on an exam question, right, just go ahead and cross out everything that's a solid or a liquid. And then look for which of these 3 options has the same number of moles of gas on both sides. In A, we've got 2 moles of gas, or 2 equivalents of gas on the left side. We've got 1 on the right side, so those are not equal. Our Kp is not going to be the same as our Kc. In B, we've got 3 on both sides, so we would expect that our Kp and our Kc are the same. And the last one, we don't have any gas on the reactant side, and we've got gas on the product side. So again, those are not going to be equal. So the correct answer here is B. There's instances where we'll want to calculate an equilibrium constant. The easiest way math-wise, for us to calculate an equilibrium constant is to measure the concentration of everything at equilibrium, so reactants and products. So for this reaction with hydrogen and iodine to form HI, if we know the concentrations at equilibrium, because they're given to us, we can calculate Kc pretty quickly. So we'll need to write our equilibrium expression. So we do concentration of the products raised to their coefficients over the concentration of the reactants. And since we have numbers for what these concentrations are, we can just plug the numbers in, put it in our calculator, and we've got our answer. So 0.78 squared over 0.11 times 0.11. I'm omitting the molarity because we're going to take the units off of our equilibrium constant anyway. So 0.78 squared divided by 0.11 squared should get an equilibrium constant of 50 or 50.28. As you might be able to imagine, given some of the resounding success that we've had in labs, it can be difficult to measure the concentration of one thing in some instances, much less three things. So this is unlikely that we'll have a situation where we can nicely and neatly measure concentrations for everything. One nice thing about measuring all the concentrations at equilibrium is you don't have to have a particular starting amount. So what we're looking at here is a table that's got that same reaction but with different starting states. So in one state we start with some amount of reactants, in another we start with just products, in another we start with all three things, and so on and so forth, a bunch of different permutations. And in each and every one of these cases, our equilibrium concentrations comes out to be slightly different, but since we got it at equilibrium, our equilibrium constant is the same for all of them at just around 50. So that's nice, we don't have to use a particular amount. But as I said, it can be a little bit difficult to measure the concentration of all three things, and so we have this tool called an ICE table, initial change equilibrium, that can help us keep track of concentrations based on stoichiometry. So it's like a little puzzle that we get to solve based on some things that we know. And the nice thing about using an ICE table using this method is that we only have to know the concentration of maybe one thing at equilibrium, as well as our starting state, which we should know how much we put in, and then we can calculate the rest if we know the equation. All right, so we've got our balanced chemical equation, A in equilibrium with 2B. We've got our initial concentrations. We started with some A. We've got an equilibrium concentration for A. Maybe A is just easier to measure. The change from the initial to the equilibrium for A was minus 0.25. So if we lost 0.25 A, how much B would we have gained? We've got a coefficient of 2, so we would have gained twice as much, so plus 0.50. So minus 2.5 A, it's 2B for every 1 A. We can do a stoichiometry if we want to. And somewhere we get to introduce a negative, probably in our conversion factor. All right, so from our change in A, we figured out how much B must have been created by losing that much A. And then we add that to our initial amount, and we've got 0.50 units for our equilibrium concentration of B. So the strategy for these, generally, for this style of ice table, we'll figure out the change for one of them, use stoichiometry to figure out all the other change values, and then just do a little bit of relatively simple algebra to figure out our equilibrium or initial concentrations. The reaction shown is carried out with initial concentrations of CO and H2. At equilibrium, the concentration of methanol is 0.11 molar. Find the equilibrium constant. So this is another instance where we'll use an ice table. So we have to set up initial, change, equilibrium, and we can put columns in for each of our chemicals that participate. Something like this. It doesn't have to be fancy. You don't even necessarily need to draw in the grid. I just thought it might be nice. All right, so information that we're given. We've got initial concentrations of CO at 0.27 molar. For H2, it's 0.49 molar. At equilibrium, methanol concentration is 0.11 molar. Another thing that we have to do sometimes with these is make some assumptions. So we're not told that we don't have any methanol, but we're not told that we have methanol, right? So we're just going to assume that we don't have any methanol to start with, the CH3OH. So we're going to assume that it's 0 since the initial concentration wasn't mentioned. If we don't do that, then it's unsolvable. All right, so we can figure out what our change of CH3OH was. We added 0.11 molar CH3OH. Looking at the stoichiometry in our balanced equation, we've got a 1-to-1 ratio between CH3OH and CO, carbon monoxide. So we will have lost the same amount of carbon monoxide. And we have a 1-to-2 ratio between CH3OH and H2. So we'll have lost double the concentration in H2. And then we can find our equilibrium concentration. So 0.16 molar. We're losing 0.22 molar for our H2. So 0.27 molar. And then we're going to use our equilibrium concentrations in our equilibrium constant expression that we get to come up with. if you can look at the reaction and just write out, like you can see it in your brain and you just want to go straight to numbers, that's fine with me. I don't think you have to necessarily write out the expression before you put numbers into it. And I'm just going to leave off the molars. And I get a value of 9.4 that I hopefully didn't screw up. Questions about the process of using the ice table in this circumstance?
Why is our hydrogen gas value squared?
The hydrogen gas value is squared because of the coefficient of 2 in the balanced equation. Other questions? All right, this reaction is carried out with an initial concentration of methane that's given. At equilibrium, the H2 concentration is also given. Find the equilibrium constant. And I will give this one to you to work through. All right, I'm just going to start putting together my ice table so that save that time later. All right, our ice table. So we've got initial concentrations of 0 for our products. Since they're not mentioned, again, that's assumed. Our change then for our H2 is where we're going to start. So we gained 0.012 molar of our H2. Our ratio of H2 to C2H2 is going to take our change of H2 to our change of C2H2. So 0.012 H2 to C2H2, we've got 3. I forgot the little 2. So 0.004 is our change for C2H2. If you want to do that in your head, I'm perfectly fine with that. So our change for C2H2 is positive 0.004. And then our ratio of C2H2 to CH4 is 1 to 2. So our change is going to be twice as big for CH4. It's also going to be negative since it's a reactant, so minus 0.008 for our methane. And then we can calculate our equilibrium concentrations. Then we'll take our equilibrium concentrations and plug those into our Kc. So we'll have 0.004 times 0.012 cubed over 0.079 squared. So it's 1.1 times 10 to the, I think it's minus 7, 6. Questions? All right, so that's our intro to ice tables. Another factor that comes up when we're doing stuff with equilibrium is we might know that or want to check if a reaction is at equilibrium, so we might be able to sample one of our reactants or all of our reactants and figure out kind of what the state is at present. We might know what the equilibrium constant is for that reaction, and we want to see like how far or how close we are to that equilibrium constant, that equilibrium state. The reaction quotient, a quotient is just the result of division. So like a product is what you get when you multiply stuff. The quotient is just the result of when you divide. The reaction quotient with QC or QP is calculated the same way as the equilibrium constant, but it's not at equilibrium. So same equation as Kc or Kp, but not necessarily at equilibrium. So this is a way of checking on the status of our equilibrium. If Q and K are the same, then that means we're at equilibrium. If Q is larger than K, that means something. If Q is smaller than K, that means something else. And here is a graph. So in our graph, we have concentration in units of molarity on the x-axis. On the left, we're all reactants. On the right, we're all products. So this is sort of relative amounts of things. Our two things here are A and B. So on the left, it's all reactants. It's all A. On the right, we have no A, and it's all B. And we have our Q or K value on the y-axis. This red line is K. So when our Q, that's this line that I almost followed well, this curved line, this is our Q value at any given set of concentrations. If we are below or to the left of where these lines intersect, then the reaction is going to continue to run up this curve. If we're past it, it's going to run down the curve. So wherever we are on this Q curve, it's going to converge on or move towards, over time, that K value. So if we are up in this upper section, that means that we've got more product than reactant than we need to at equilibrium, and so it's going to decrease concentration of B, increase concentration of A, causing that value to come down. If we're below it, we've got more reactant than we're supposed to relative to product, so it's going to slide up. So the three possible options is that our Q is less than K. Remember that all of these are products over reactants. So if Q is smaller than the equilibrium constant, that means that we've got more reactant or less product, or both. It would be both. Then at our K value, so it's going to continue in the forward direction. If our Q is bigger than our K value, then that means we have more product. Let me write use up instead. So we're going to use up some of our products as the reaction continues to work towards equilibrium. And if they're the same, then we're at equilibrium. You can measure Q however many times you want. It should have like a continuously sliding scale of values as the reaction occurs. All right, so let's consider this reaction and its equilibrium constant. We have a reaction mixture that contains some concentrations of both things. Let's calculate a QC. Remember, a QC equation is the same as our K equation, our equilibrium constant equation. And we can plug in the values that were given to us. So our reaction quotient is 0.0196 and some other stuff. How does that compare to our equilibrium constant? So yeah, so our QC is greater than our KC. the two ways you can think of that, since these are ratios, is our top number is bigger than our bottom number should be, right? We've got extra on the top or not enough on the bottom. That's making our Q bigger than our K. So this top number needs to come down, the bottom number needs to come up to shrink that. So we're going to remove some product. And add reactant to get to equilibrium. So that would be a shift left. We're going to be moving towards the reactants from the reaction quotient that we have. For this reaction, we initially have pressures, partial pressures of 1 atmosphere of both. If our Kp is 0.15, which statement is true of the reaction mixture before the reaction occurs? Are we at equilibrium? Is the reaction going to proceed towards the products? Is it going to proceed towards the reactants? We can calculate what our reaction quotient is at this starting state. 1 atmosphere, 1 atmosphere. Be 1 squared over 1, which is 1. So if our Q is 1 and our Kp is 0.15, our Q is larger, the reaction is going to proceed to the left. Same as with the previous example. Questions about reaction quotients? All right. Moving back to equilibrium concentrations. It can be helpful in circumstances to calculate equilibrium concentrations of reactants or products if we know the equilibrium constants. There's 2 basic types of this. The one where we have K and all but one equilibrium concentration is known. So we just would take our, this is backwards probably, but right, for example, in 1, we would know what K is, we would know what A is, and then we can calculate what B would be there. That's just going to be kind of basic algebra stuff. However, there's also instances where we'll have our equilibrium constant and initial concentrations, only initial concentrations are known. This is probably much more likely. It's easier to know how much you started with than it is to figure out equilibrium concentrations. And for those instances, we get to use our best friend ice tables. So we'll start off with that first case where we know everything except for one of the equilibrium concentrations. So for diatomic iodine, decomposing to monatomic iodine atoms, we know the Kc, and we know in an equilibrium mixture the concentration of I2 is 0.10 molar. We're going to start by writing out our Kc, our equilibrium constant expression. Concentration of iodine squared over concentration of the other form of iodine. We'll solve for the concentration of monatomic iodine. You can, of course, put numbers in before you solve. All right, so after one algebra step, we arrive at the concentration of monatomic iodine squared equals concentration of diatomic or molecular iodine times the Kc. And then we square root both sides. That'll get rid of the squared on our concentration. And our solution is square root of the concentration of diatomic or molecular iodine times Kc. Plug our numbers in. Put it in the calculator, press enter. So I got a value of 0.032 molar for the concentration of monatomic iodine. Questions about that solution process? At worst, I would expect that you might have to do a cube root, probably not a quartic root. Your calculator would do all that for you, so as long as you can do the rearrangement, you should be fine. For the reaction given, Kc is 4. A reaction mixture at equilibrium contains 1 molar A. What is the concentration of B in the reaction mixture? I'll give you a little bit of time to solve that. All right, Kc, which is equal to 4.0, is equal to concentration B squared over the concentration of A, which is 1. Since it's 1, you can just ignore it. So 4.0 equals concentration B squared, square root both sides. Concentration of B should be 2. This is, I think most people would agree, the easier type of solution. So let's look at our other one. The more common type of calculation is going to be the one where we have to use ice tables. So for this style of problem, we're given K and initial concentrations. And we have to use a particular procedure to solve these problems. So we're going to set up an initial change equilibrium ice table with our initial concentrations written in. We'll represent the changes in terms of x. So we're going to write in a variable. And then we'll figure out the equilibrium concentrations in terms of x. So we'll have initial concentration plus some amount of x, or initial concentration minus some amount of x. And then we plug them into the equilibrium expression and solve. That's our thing that looks like this for our generic. So let's look at what this looks like. So here's an example with A and 2B when K is 0.33 and the concentration of A is initially 1 molar. So in our ice table, we would have started off with just the initial amounts. And then we represent the change relative to their stoichiometric term, their coefficient. So A has a coefficient of 1. It's going to be used up at a rate of minus x. So we plug in a minus x. Our product, B, has a coefficient of 2. So we plug in a plus 2x. It's going to gain 2x. And then at equilibrium, it's our initial plus or minus our change. So for concentration of A, 1 minus x. For concentration of B, 2x. And then we plug it into our K expression. And it was at this point in time, when I was reviewing the slides, that I remembered, oh yeah, that's why I have a negative gut reaction to ice tables. So let's look at what this looks like. Our K is going to be concentration B squared over the concentration of A. Nice and simple. We're going to plug in values for each of these. So we'll have on the top 2x, that's squared. And on the bottom, we're going to have 1.0 minus x. So 0.33 equals 4x squared over 1 minus x. and we need to solve for x. So let's rearrange it a little bit. I'm going to move the 1 minus x over to the left side. I'm going to break it down as simply in as many steps as it takes. All right, so after doing some rearrangement, doing some algebra, we get this lovely mess. 0.33 minus 0.33x equals 4x squared. And we can get everything onto one side. So moving everything from the left side to the right side, we get 0 equals 4x squared plus 0.33x minus 0.33. Who remembers how to solve for x here? Yeah, we get to use the quadratic equation. Isn't that fun? And this should be blocked out. It should have been blocked out already. All right, so we get to use the quadratic equation. Change my font size back. The fun thing about the quadratic equation is that we get two solutions, since we've got an x squared in there. So we have to pick the value of x that works. So we get to plug in all sorts of fun stuff. Our generic equation for the quadratic equation, ax squared plus bx plus c equals 0. And it's negative b plus or minus the square root of b squared minus 4ac over 2a to find the solutions. So you do one with plus, you do one with minus. And then you pick the winner. So it's a lot of fun. Questions about the process? I ran out of room, so I'm not going to solve the example. But we've got another one that's right after it. All right. Let's do one totally from scratch, and I'll try not to run out of room this time, so I'll be a little bit more hasty about coming up with the quadratic form. This reaction starts only with the product, and it even tells us no reactants. Nice. So we have to come up with our ice table. So we'll list out each of our chemical species. We put our initial change and equilibrium down the left side as our rows. We had 0 for our N2 and our O2, 0.0100 for our NO. Our change, since we're going to be producing N2 and O2, we're moving in the backwards direction. We're going to be gaining one equivalent of each of our reactants, our N2 and our O2, and we're going to be losing two equivalents of our NO, minus 2x. The 2 because of the 2 coefficient. So then our equilibrium values are x, x, and 0.0100 minus 2x. Questions about the ice table part?
Why are the reactants positive instead of negative on this one?
The reactants are positive because we're starting with NO. We don't have any reactants. So our initial concentrations have to go up for our reactants. So we're working right to left instead of pushing left to right. So we can plug these all in. K is 0.0100 minus 2x, and that is squared. That whole term is squared over x times x. So that'll also be x squared. So we get to use our old friend, FOIL. First outside, inside last. So 0.0100 minus 2x times the same thing. Multiply our firsts. Multiply our outsides and our insides. So we're going to be negative 0.02x twice. And our last, purple might show up well. Yeah, purple shows up okay. So plus 4x squared. So k, which is a number, let's write that number in. 0.055 equals this. Oh, the joys of algebra. We're going to move the x squared out from the denominator so that we can solve stuff. And we'll end up with 0 equals 3.945x squared minus 0.04x plus 0.0001. And then the tedium begins. So we get to use our quadratic equation. We'll write that up at the top. So one of our, well, actually I can just write them both. Our B is negative 0.04. So 0.04 plus or minus the square root of negative 0.04 squared minus part of our equation 4 times 3.945 times 0.0001 all over 2, which is part of our equation, times 3.945. And assuming we didn't do anything incorrectly, we should get a reasonable number. So our two solutions one of our solutions is 0.004475. Our other solution, 0.00566. In the previous one, I believe you get a negative number. In this example, one of them's a negative number, so obviously you don't pick that one. Or maybe it's not obvious, but you're not going to pick that one. You use the positive one. In this case, we got two positive numbers. And so how do we choose which one of these is our correct solution? Because there can be only one. So the way that we pick our solution is we can plug it in. We know our initial concentration of NO. We know that we subtract 2x. One of these solutions works, the other one doesn't. So if we look at our solution 1, we subtract 2 times this, that's 0.00895. That works. Our solution 2, 0.005, if we double that, that'll be bigger than our 0.01. So I'll bleed into the next page here. I put in the wrong thing. 0, 1, 1. We would round it to. That's with solution 1. For solution 2, we'd get negative concentration, equilibrium concentration. We can't have a negative concentration, so our solution, correct solution here is solution 1. So then we can plug in solution 1 to each of our x values to get our answer. Yeah, cool. Wanted to put that there. You should have gotten 0.0045 molar for both of the reactants, which, if you'll notice, is our solution 1, rounded to 2 sig figs, and 0.0011 molar, which is what we got when we calculated that for solution 1. How are we feeling? All right. Your turn. Consider the following reaction. It initially contains only the reactant and no product. Find the equilibrium concentrations. I'll give you 5 minutes. Hopefully that's enough time. starting to fill out the ice table. All right, we've got the K part of it up there now. And then we're going to rearrange that to get into a quadratic form. So there's our quadratic. And then we can solve our quadratic. Just write it in for fun. Right, so that's our quadratic. We do one where we subtract. That's what the plus negative is. We do one where we add, we do one where we subtract. So we get two solutions, x1 and x2. One of those solutions is 0.02038 dot dot dot. The other solution is minus 0.1103 dot dot dot. So we're going to use the positive one. So then we plug this in. To the E row of our ice table. So our concentration at equilibrium for our N2O4 should be 0.0046-ish. And then 2 times that value oh goodness. All right, 0.041-ish. A little bit messy. Questions?
So you don't use the other value because it's negative?
We can't use the other value, yeah, because it's negative. Since our NO2 concentration increased by 2x, that means it would be 2x. If we plugged in a negative value for x, we'd get a negative number. You can't have a negative concentration.
But if it was a negative, then it would work?
If it wasn't negative, then we would need to check both of them because only one of them can work.
Okay.
Since there's only one equilibrium state,
Yeah.
we can only have one set of equilibrium conditions given an initial value. Other questions about this?
What if we rounded to 0.05?
What if you rounded to 0.005?
No, it's like 0.005, yeah.
I mean, I just wouldn't do that.
Are we going to consider like sig figs for this or no? Because like we start with 2 and
I don't think it's super important, but I would say probably just however many sig figs you started with, you might want to end with. So I could maybe add another sig fig. All right, that'll do it for today.